Hello everybody, today I'm gonna talk about covariance and its improved version, correlation. And I'm going to explain everything to you in a very simple visual way. And hopefully after watching this video you'll be able to guess the value of correlation just by looking at the graph. So I will do it right now. I think here there will be definitely negative correlation, I think pretty strong, and I click submit. And I can compare my guess with real correlation, and I was pretty close, and you can see a whole bunch of accessories on the graph. I will talk about it later. Let's take another graph, similar situation, I think even more correlation we have right here, and I will click submit. And after 5 guesses I have an average error of 0.054, which is just simply how on average I was mistaken. And I'm really curious of what your results will be, so share that in a comment section. And I'm really curious if anybody can beat this score. The link to that is in the description below. You just simply click runtime, run it all. You scroll down and you can play it. If you want to play again, you can click this button and you will play the game all over again. So just to give you a basic idea of what correlation measures, it tells us the value between -1 and 1. That describes the connection between data. So for example, we have NBA players' height and weight. Okay, so every dot is a player. This is Michael Jordan, maybe. Here he's 198 centimeters and 96 kilo. Every dot is a different player. And you can see there is a trend that we could draw a red line that the points the players oscillated by. And the red line is pointed upwards. So if we go right, we go up. If the height grows, the weight grows. That's why we have a correlation positive, okay? Correlation positive, so here. Here we have an example of soccer players' height and weight. And we see a similar situation, just the players are much closer to the red line. So we see the trend much more clearly. Okay, so we are more sure that the taller person would be a heavier person, and we say correlation is positive, but it's bigger. Okay, so the correlation is positive when you go right and up. Okay, so one thing grows, the other thing grows, and the closer you are to the trend line, the bigger the correlation is. Okay, here we have an example of no correlation. NBA players' height and phone battery percentage. What does that even mean? How could those two things be connected? Like, height doesn't really have anything to do with phone battery percentage. So Michael Jackson would have 46% of battery in his iPhone. And we can see that the dots are everywhere. We can even draw this red line, the line of trend, and the dots they don't have a trend. So the correlation is 0 because we see a lack of connection. There is no connection between those two variables. In this case, when we have apartment rent price and distance to the city center, we all know that the closer we are to the city center, the more expensive is apartment because it's a better placement of that apartment. And we can see a negative correlation, -0.77. Because if the price goes up, the distance goes down, okay? So one thing goes up, the other thing must go down, okay? In these cases, both were up, and we have a positive correlation. And if the prices would be, if those apartments would be closer to the red line, we would have a stronger correlation, so closer to -1, okay? So if you don't have any connection, you're at 0. If you have the stronger connection you are, the points are closer to the red line. And if the line is pointed upwards, you have a positive connection. If the line is pointed downwards, so if you go right, you go down, one thing grows, the other drops, then you have a negative correlation. So what correlation we have on that graph? We have boxers with height and weight. And boxers usually fight in weight divisions, in this case up to 82 kilo. And we have a positive pointed upwards line. If it's pointed upwards, then we have a positive correlation. The dots are very close to the red line. We can estimate the height of a person like plus minus 2 kilo, which is very good. So the correlation is probably very big, like 0.08, 0.9, right? No, the correlation is surprisingly small. And why is that? Because this is very misleading graph. Here you have the same graph. This is the same graph as this, but it's properly drawn. As you can see, we have an axis of weight is spread from 65 kilo to 95 kilo, but we don't need that. It's enough that we do from 78 to 82, because your spread of the data should be as wide as it is tall. And in this case, we definitely don't do that. This distance is much smaller than this distance. But in this case, this is correctly draw data, and we can easily say, if we would look at it, there is maybe a correlation, but it's very, very small, okay? I don't know if you will see it on your screens, but if you will take any spread of the data, and if you would just simply squash it, the dots will be closer to the red line, okay? See, they are closer now, probably twice to the red line. So when you estimate visually correlation, you have to be very, very careful for a small angles, or very high angles for that matter. Let's go back to this example. So if you get a very high angle, by the way, this is also in this link. You have all of accessories here, and you can manipulate the graph. You have spread of the data. It works like this. The line will be farther away. You have number of dots. But when you have the spread of data like this, and you have very high angle, it's really hard to say anything because we don't see the reality of that graph. You can always click here. This is standardized data. This is something very similar that I showed you on these images. Just it's a bit different. I will talk about it more later. But this is correct vision of data. Okay? You should always remember, as wide as it is tall. So remember, if your line is getting flatter or pointed up, you have to estimate the correlation differently. So here we have 53 degrees of a slope, and the correlation is 95. If we would go up to 83, for example, the correlation would drop dramatically, okay? If you would go very close to 0, the correlation would drop dramatically also. And the spread of the data, the distance, average distance from the red line didn't change. So you have to be careful. If you have a very flat or very upwards line, the dots must be even closer to the red line to have a bigger correlation. But remember, you have that link in description, and the best way to learn it is just to play with it. Go there and find some few compositions of parameters, and you will get much better at it. But I think there exists even better way of looking at correlation. Now, I will just give you a hint. I will talk about it later in the video, but maybe some of you will figure it out only by this. Okay, so we finally know how to visually estimate correlation, but how do we calculate it? And I know what you may think. This is a little bit scary. There's a lot of formulas, but they are pretty easy if you explain them visually. So we want to calculate correlation, and this is the formula for correlation. Okay, this one. I don't really like this one. And as you can see, we have to first get the covariance to calculate correlation. And we will focus on that. This is a formula for correlation, but let me just give you a simple idea of what the correlation is. You can see here on the graph that we found a new center of a coordinate system. This is a yellow dot. That is simply average weight and average height of those players, okay? And the covariance is average surface that the points make with new coordinate system. And to explain it a little bit better, we have to dive into the formulas. They look scary, but they are pretty easy. This one is simply average height. That's it. If you never saw this sign, this is simply saying add everything from the first to the last. Add everything of those. X is usually here, right? Which is height. So we have to add all heights that we see. So 170 plus 171 plus 172 and so on. And we divide it by number of players. And we have average height. We do the same with weight, which is Y. Y is usually here, so it's a weight. And we get this and this. And as you can see, we use it in the formula for covariance. Okay? And in this formula for covariance, we see that sign again. It means that for all of those, we have to add from the first to the last. And this is a formula for the surface. And don't worry, it will become clear in a moment. So let's take a first player. This is Mark, this green dot. Okay? And Mark is 184 centimeters and 84 kilo. Okay? And we want to calculate the surface of this, the surface that this dot makes. So according to what we can see here, and according to this formula, we will put his height, 184, minus average height, okay, which is this, and also this line, okay. So here we have 4 centimeters, okay, from this point to this point. Now we will subtract from his weight, 84 kilo, 80 kilo, okay, and his surface will be 16, because 4 multiplied by 4 is 16, and units, centimeters, kilograms, okay? And we do the same thing for every single point. So the next guy is Jim. And he has surface of 18 because he has 6 centimeters here, 3 kilograms here. And maybe the next guy will be maybe Steve. And this is something that you have to remember. In second and in fourth quarter, the surfaces are negative. That's why they are in red, and those were in green. This is negative surface because you can see 181 minus 180 is 1 centimeter, okay? But 78 minus 80 is minus 2. So negative y and positive x give us negative surface of minus 2. And this is super crucial, okay? So let's write our surfaces till now. So we had 16 for Mark, we had 18 for Steve, and we had minus 2 for Jim or Steve. I don't remember. Doesn't matter. And you have to calculate all of those surfaces and divide them by number of players. Let's say that there's 20 of them. I don't know how many is there. And you have the covariance, which is the average surface, considering all of those surfaces, positive and negative. Let's say 10 centimeters kilograms. Okay, so we got this covariance of plus 10 kilograms centimeters. Is a positive correlation. So what? What we can tell from that value? If you tell it to somebody that you found the covariance of height and weight of boxers and it's 10 kilograms centimeters, that person would have no idea what you're talking about. Like, from that, you can imagine how the graph would look like. If you would tell the correlation, maybe 0.8, they would know how that correlation looks like. But this is uninterpretable. So to change covariance into something that people understand, we have to divide it by standard deviation. Okay, we will talk about it in a minute. From the covariance itself, you can only tell the correlation is from 0 to 1. It's positive, okay? This value is positive, so the correlation must be positive. But you don't know where that number is. It's 0.1, it's 0.9, you don't know that. And if you think about it, when there's more green dots than the red one, the surface becomes green, the average surface becomes green. And the line of trend goes from the first to the third quarter, so like this. It means upwards, okay? So that's why the correlation is positive when the covariance is positive. And now I will talk about standard deviation and normal distribution. And soon I will make a separate video for it, so if you want to see it, make sure to subscribe. But for now, just to give you a basic idea of what it is. Normal distribution is when you draw a spread of heights, you would have a shape like this, maybe more like this. This is similar to a bell. Okay, it's called bell curve. And it can be taller, it can be smaller, but if it looks like that, it's normal distribution. And standard deviation tells you of how on average, in simple words, this is a true formula, in simple words it tells you how on average the height differs from the average height. So you would say, yeah, those players with the black line, those players are on average 180 centimeters plus minus 1 centimeters. That plus minus 1 centimeters is basically standard deviation. So we can see we have here 1 centimeter, okay? This is 1 centimeter. So the standard deviation is 1 centimeter. But if you would see on this graph, we have few people that are 180, but also a lot of people that are over 185 and below 175 in the red line, okay? We don't have that in the black line. So in the red line, the spread of the data, the variety of heights is much bigger, okay? It's 5 centimeters. See? Here the graph is smaller but wider, so you have a lot of heights of players, tall, small, average, and here you have basically in the black one, everyone the same. And now we will go again to the link in the description below and connect all the information that we got up till now. So we will draw a few accessories on the graph. We will plot correlation, covariance, and standard deviation as something new, which is called covariance rectangles, because that's how I named it. This green rectangles tells you the covariance. This is exactly covariance, so 10.62. This is the surface of this green rectangle, okay? And as you can see, the farther the dots are from the red line, this rectangle becomes smaller and smaller. The closer they are, it becomes bigger and bigger, okay? In this case, it's almost at maximum level, because this blue rectangle is the maximum covariance that we can get, okay? Maximum surface. Okay, and this blue rectangle is made by standard deviation of both dimensions. So standard deviation of x data, which is height. So the average players differs by 3.78 centimeters and 3.65 kilograms. Okay, and this is maximum surface that we can get. Okay, because the covariance, it's not enough. We have to compare the surface to the spread of the data, okay? Because right now we can see the covariance is 5.7 and maybe somebody think it's a big number, there would be a big correlation, but it actually isn't. We always have to compare this surface up to surface that the data is spread, okay? So we can see this is pretty small compared to the spread of the data. Okay, and this is exactly the formula for correlation. So we have to divide covariance by standard deviation. So we literally dividing this surface over this surface. Okay, this green surface over this blue. And we can see it's kind of a quarter, so 25%, and we're pretty close. So this is how the correlation, standard deviation, and correlation comes together to make a covariance. Maybe we'll see an example with a negative correlation. It works the same, okay? But now we have a negative covariance. You can see minus 5.5, okay? So we have a negative correlation. And we still do basically exactly the same thing. So we divide this negative surface over the perfect covariance, which would be standard deviation of 4 points of those values, okay? If you go to 0, the points will line up perfectly in to give us -1 correlation, and the green rectangle and the blue rectangle will be the same, Okay, so the standard deviation of x multiplied by this would give us exactly the same as this. That's why the correlation is -1. And I wanted to tell you something about this interesting function, which is standardized. You have a standardized data. It's really useful when you have a very horizontal, very vertical spread of the data. It makes it clear to see visually what the correlation is. And what is this standardization? It's a pretty simple thing. If you think about it, I could measure height in feet. I could measure height in inches, meters, millimeters, everything. But in my opinion, the best unit is simply lack of units. Okay, and this is the basic idea behind standardization. And what we do to get that standardized data, we apply this formula. So we shift the data from the center of the mean of 180 centimeters to 0. We simply grab this. This is as simple as that. Simply grab this and move it to 0. Okay. Now we divide it by standard deviation. So the standard deviation was like 3.7. So we have to make it 1. Okay. I don't know if it's 1, but you get what I'm saying. So from the spread of the data that we had here, we have data that is of a mean 1 and standard deviation of the mean 0 and standard deviation of the mean 1. Okay, and it makes everything much simpler because you will always have this beautiful graph when the standard deviation is 1, standard deviation of x and y. So the covariance is also correlation. Because usually how we apply this formula that we saw, it's we first make a covariance, calculate covariance, then we divide it by standard deviation. But in my opinion, the better way would be to standardize data first and then make a correlation. Everything makes more sense, at least for me. I don't know if for you. Because we don't really care what numbers are here. Centimeters, feet, it doesn't matter. We only look at the graph. And in this case, with standardization, we make sure that the data is as wide as it is tall. And I said it is super crucial to have a good visual representation. And standardization, I think it's overlooked today. And in many algorithms, if you don't use standardized data, you will have wrong results. But this is a topic for another video. Correlation is a great tool, no doubt, but can we always use this correlation? No. The correlation that we used in this video is a specific version. It's linear correlation, and it's called Pearson correlation. So it only applies when you have a linear connection between the data. So if you can draw a straight line through it. So if you have a line like here or here, if you have something like ellipse, or if you have something even like a circle, then it's okay to use the correlation, okay? If you have something else, like here, we can clearly see there is a trend. Everything here has a shape, and everything has a correlation of 0, but you shouldn't even look at those values. It doesn't tell you anything useful. It only tells you useful if it's a line, ellipse, or a circle. In those cases, you shouldn't even look at it because the correlation will always give you some value because it's a mathematical tool. It will always spit out something. So if you have something like this, maybe the correlation goes like, maybe the line goes like this. The correlation will give you some value. I don't know, maybe 0.2, but you shouldn't even look at this if it's not a straight line. And we have to be realistic, okay? In real life, we don't have a perfect linear correlation, so a perfectly straight line. But if you have something like maybe this with a slight curve, okay, then it's okay. Then it's okay to use this correlation. So now you understand how to mathematically calculate a correlation and you know how to visually estimate it. All it's left is just to test this theory in practice. So take the test of 5 guesses and see what your average error would be. Mine is 0.044. If you're under 0.3, I think it's okay. I think it's really good. So take the test, share it in comment section. And I want to be honest with you, this is my first video on YouTube. So if you like my content, you would like to see more of that, just let me know. give me a thumbs up, give me a subscription. Maybe write in a comment section what you would like to see as a next episode. Basically everything from machine learning. So I really thank you for watching and hopefully see you soon. Bye.